Hello everyone. This is going to be our attempt at doing a video on a non-R related concept, on a statistics concept. See how this goes. So we're going to look at distributions for a moment. And here we have that histogram we looked at earlier in the quarter, which is a histogram of heights of people 18 and older in the US measured in inches. And again, this is not the real histogram of heights. This is a histogram that I constructed that was supposed to roughly model what heights in the US look like. So let's imagine this indicates the heights of all people over 18 in the United States. All right, so we talked earlier about measures of center, and we're going to move forward quickly into measures of spread. It's useful when we look at that histogram to be able to identify what we think the center of this histogram is. And again, there are a number of definitions we'll move to in a second. And in addition, something about the width of the histogram. It is useful to understand, again, roughly how wide this histogram is. And this will also be useful when we think back to the sampling distributions we've been talking about, right? Often when we calculate p-values or do statistical testing, it's useful to think about how far into the tail we are, and sometimes we can relate that to a concept of width of a histogram. Great, so for measures of center, we discussed this before. We had the median value, the mode, and the mean as three fairly usual measures of center. The median is that value such that exactly half of the population is above it and half is below it. So again, if we go back to this histogram, it would be the point such that, again, half of the mass, the area of the histogram is to the right, and half of the area of the histogram is to the left. The mode is the highest point on our histogram. It's the most likely value. So again, here it might be the x value around 65-ish. And the mean is actually generally the most common measure used, and it's basically the sum of all of the values in the population divided by the population size. So that's formally how you would calculate it. Intuitively, you can think of it as the point at the bottom of this histogram where it would balance if we sort of had it act like a seesaw. So again, you can imagine for the median, if I took some points out here and I just moved them way far to the right, that's not going to change the median. That will change the mean though, because it's going to change that sort of center of gravity. So you can think of it almost as the center of gravity of the histogram. Excellent. So we've covered these centers of measures of center. We're going to move on now to measures of spread. How do we think about or quantify the width of that histogram? So one way we've talked about before is the interquartile range, and this is the distance between the 75th and 25th quantiles, or the third and first quartiles. And, you know, there's no reason you have to use 75th and 25th to measure the width of a distribution or a histogram. In this case, that is the definition of the interquartile range. But if you wanted to characterize the width in terms of the 95th and 5th quantiles, that would be actually probably a very reasonable thing to do. That would give you a bigger width than the interquartile range, but you could think about using maybe other quantiles in this characterization instead. And now if we go back to this height data for a second, I plotted a blue line at the 75th quantile. So 25% of the data lies to the right of this, or the population lies to the right, 75% lies to the left. And another blue line at the 25th quantile, or the first quartile. Here again, 75% of the population lies to the right, 25% lies to the left. And the distance between these two is the interquartile range. So this was just a way to visualize. And in this example, the interquartile range is 5.8. And in fact, the median will lie in between these two. Maybe not precisely at the center of those two, but again, roughly in between. And for a symmetric distribution, it will lie exactly at the center of those two. Okay, so we have this measure, interquartile range. There are two other measures we're going to discuss. One is the mean absolute deviation, and finally the standard deviation, which is maybe the one people are most familiar with, but it's also, I think, the most unintuitive. So another thing we could do is look at this mean absolute deviation measure, and this is just the average distance between the center of our histogram and each of the observations or each of the people in the histogram. Or in the population. So let's think about what I mean by this and how we calculate it. Let's imagine, rather than looking at the heights of everyone, we had this tiny data set of 4 people, and we wanted to calculate the mean absolute deviation in this data set. The first thing we would do is calculate the center of the distribution, In this case, we would add these four numbers together, or the center of our sample, divide by the total number of observations 4, and get that the mean, or this measure of the center we're using, is 64 inches. So that's the mean height. Then for each of the 4 people in our sample, or in this case, maybe we think of it as our tiny population, we can calculate the distance from their heights to the mean height, from their height to the center. So the person who's 60 inches, their distance to the center is 4 inches. The person who's 63 inches, their distance to the center is 1 inch. 65 inches, their distance is 1 inch. 67 inches, their distance is 3 inches. And then we average all of those, and we would get that the mean absolute deviation is 2.25 inches. On average, people are 2.25 inches away from that center. Notice when we take the distance, we remove the negative sign if there is a negative sign. It would sort of be like if we were trying to understand a little village, and we said, in general, how far are people from that village center? How far will they have to walk to get from their house to the village center, right? You would look at the distance for each person. You wouldn't really have positives and negatives. And so that's the same thing that's going on here. We want sort of the distance, the average distance between each of the people and the center of our distribution. Excellent. So if we go back to the height data for a second, we can now visualize the mean absolute deviation here. Here, for the interquantile range, there's this symmetry. We look at the 75th quantile and the 25th and we subtract them. For the mean absolute deviation, we don't really have that symmetry. So here I plotted the median, though I could easily have plotted the mean, and I have the median plus the mean absolute deviation. So this is sort of saying, and really it should have been the mean plus the mean absolute deviation, but it's sort of saying on average, the distance between the solid line and the dotted line is how far we expect to see an observation in our population from its center, right? That's the sort of average distance between an observation and its center. So, and in this case, that value is 4.3. Great. So let's think about comparing this interquartile range and the mean absolute deviation. So let's imagine that we have a small number of huge outliers. We have a small group of people who are 20 feet tall, right? Will this have more of an effect on our interquartile range or on our mean absolute deviation? So I'm going to pause for a second, and you can pause the video and think about this one, and then return and listen to what I have to say. So this is going to have a larger effect on the mean absolute deviation. For the interquartile range, if we take our tallest people and just make them a little taller, it's actually not going to end up changing our 75th or 25th quantiles at all, so long as it's only a small number of people. So in fact, our interquantile range is really robust to these outliers, which can be a good thing, but it can also mean that we maybe don't accurately measure our spread if we have a small number of really large values and we'd like to include that in our measured spread. The mean absolute deviation, on the other hand, would include those points, and they would be in this average distance, right? They would have large contributions to the average distance between the mean and each observation. So another important question is, what happens to these measures if we change our scale? So if we had initially measured height in inches and then moved to height in centimeters, all of our measurements would be multiplied by, this shows my ignorance, some number, I'm going to say 2.5, because I believe there are 2.5 centimeters per inch, but all of the numbers in our data set would be multiplied by 2.5, our mean would be multiplied by 2.5, our quantiles would be multiplied by 2.5, and it turns out both our interquartile range and our mean absolute deviation would be scaled by 2.5, that everything would be scaled by the same amount, and the units would change from inches to centimeters. So you can think of this like the interquantile range and the mean absolute deviation have the same units as the mean, and have the same units as actually our observations. And this is going to be important when we start talking next about standard deviations, and we'll see variances. All right, we're going to move now to the standard deviation, which is probably the most commonly taught measure of spread, but it's kind of unintuitive. I say annoying here because it's tricky to think about and understand why we use it. So again, it's actually quite similar to the mean absolute deviation with a slight twist. that again makes it a little trickier to understand intuitively why we want to use it. It turns out it's a very canonical or mathematically important or natural idea. Um, but again, you have to get a little bit into the math to understand why. And that will be saved for another video. So the standard deviation is related to something called the variance, and we're going to engage with the variance first. So recall, we just talked about this mean absolute deviation, which is the average distance between each of the observations and the mean, or the center of our distribution. The variance is like that, but with a twist, it's the average square distance between the observations and the mean. So let's see what we mean by that. So going back to our tiny example data set or population with 4 people, and their heights measured as 60, 63, 65, and 67 inches. Our center is again 64 inches, the average of all of them. The distances, again, are 4, 1, 1, and 3. So when we calculated the mean absolute deviation, what did we do? We just averaged these 4 numbers. When we calculate the variance, what we do is we square each of the numbers and then average those squared values. So 4 squared is 16, 1 squared is 1, 1 squared is 1, 3 squared is 9. So we would average the numbers 16, 1, 1, and 9, and that would result in 6.75. So again, that's how we would calculate our variance. Originally, again, we wanted the standard deviation, not the variance. So how does this work? How do we go from one to the other? The standard deviation is defined as the square root of the variance. So we take that number 6.75, we take its square root, and in this case we get 2.6. So there's something funny going on here. So we started with our original observations, we took the distance between each of them and the mean, we squared that distance, those distances, we averaged them over our population, and then we took the square root. So what's going on? Why did we maybe do that? Let's think about that a little more. But before we do that, let's look at a visualization of the standard deviation on this height data. So again, we have our histogram of heights of people 18 years and older in the US. And again, I have a line here for the median. The mean is very, very close. And my dotted line is this median plus the standard deviation. So the distance between the lines is the standard deviation, which in this case is 3.9. And it doesn't exactly tell us, the average distance between the center of our distribution and each observation, but it is something sort of like that, right? Again, this is why I like the mean absolute deviation maybe a little bit more than the standard deviation in terms of intuition, but they give us very similar pieces of information. The standard deviation, it turns out, upweights larger values ever so slightly in that calculation. All right, so standard deviation and variance. What is going on? Why does it make sense to calculate the variance first, and why does it make sense to calculate the standard deviation? So let's think about the variance to begin with. So the variance is this average distance between our observed measurements in the center. We just have to be careful. Distance now takes on a new meaning, and it is the square of the original distance we were engaging with. So it's not really an average distance, but it's an average of some transformed version of our distance between each of the observations in the center. So you can think of it kind of like the mean absolute deviation, except we're increasing the importance of extreme observations because their distances get squared. And when you square a big number, it gets huge. And when you square a little number, it gets much smaller. So again, we're like upweighting the big numbers and downweighting the little numbers, saying the variance is going to look real big if you have outlying observations as compared to the mean absolute deviation. Okay, so let's imagine variance sort of makes sense now. Why do we add this square root at the end, right? What's going on here? Why did we square things only to later square root them? And the answer is, when we talked about the interquartile range and the mean absolute deviation, there was a property that was really nice. And that property is that the units of each of those measures are the same as the original units of the data. And another way of thinking about this is that if we scale all of our observations by 2.54, moving from inches to centimeters, then we find that we know the mean and the median change by exactly 2.54, but in addition, the interquartile range and the mean absolute deviation also change by exactly 2.54. Excellent. However, when we're engaging with the variance, because we have squared things, our variance will change by 2.54 squared. So again, somehow the units are wrong. Rather than it being in units of centimeters, if we measure height in centimeters, our variance will be in units of centimeters squared. Ugh. So when we take the square root at the end, we end up making the units correct, and we also end up making sure that this measure of spread is on the same scale as the original data. So again, this is another way of saying if we take all of our measurements and scale them up by 2.54, the standard deviation also scales up by a factor of 2.54, so things sort of stay on a comparable scale. And I apologize if that's not maybe the most intuitive explanation or the most intuitive idea and the reason why we like this standard deviation. Again, I haven't really explained why one might prefer it over the mean absolute deviation, for example, although we'll discuss that as we move forward. But maybe it makes sense why the standard deviation might be preferable to the variance. Again, because it's on the scale of the original data as opposed to some weird squared scale. So again, this is just reiterating that the point is to keep the units the same, units of inches or centimeters rather than inches squared or centimeters squared. And again, later we're going to talk about a really cool theorem called the central limit theorem that a lot of statistics is based on. We haven't engaged with that yet in the class. We haven't had to. We've been thinking about other big picture ideas around testing and such. It's very common to use the standard deviation to measure the spread of a data set or histogram. I think in general, it's no better than looking at quantiles, looking at the interquartile range, and or the mean absolute deviation. And in fact, often I think those can be more informative, but the standard deviation is such a usual and natural quantity because of these other pieces that we will discuss. And here I have all three measures of spread plotted. I have a black line again at the median of the distribution, and then at the median plus each measure of spread, I have a dotted line. In blue, I have the interquartile range divided by 2, again, because somehow it's looking at this symmetric difference. In red, I have the mean absolute deviation, and in orange, I have the standard deviation, right? And we see that they're all giving similar ideas of spread. They're not, one thing to note is, they're not telling us on their own the total width of the distribution, right? You can often think of them as saying something like the distance from the center to the bulk of the distribution, or to where the distribution begins to fall off. And so sometimes to really capture the whole distribution, you might want to look at your center plus or minus 2 or 3 times your standard deviation, or plus or minus 2 or 3 times your mean absolute deviation, or plus or minus 2 or 3 times your, here I have IQR over 2. So that would be like 1.5 times your interquartile range. Great. The end.